Hello and welcome everyone. Today is day 33 of our low-level design journey and it's going to be a very practical and interesting session. We are focusing on cache systems, specifically understanding and designing two major types, LRU and LFU caches. These are fundamental building blocks behind systems that need to be fast, scalable and efficient. Let's dive in. Before we begin, let's quickly set the objectives for today's session. First, we will understand why caching is important, not just in theory, but how it impacts real-world systems. Next, we will go deep into how LRU and LFU caches work internally, their logic, structure, and real usage examples. Then we will discuss how to design these caches so that they perform with optimal time and space complexity. And finally, we will look at how caching systems are made thread-safe to work correctly even in multi-threaded environments. Imagine you run a popular restaurant. Some customers order the same dishes again and again. Instead of cooking everything from scratch each time, what if you could partially prepare your most popular items in advance? That's what caching does for computing systems. It keeps frequently requested data ready, significantly reducing time to serve users. Caching boosts system performance, cuts down load on databases, and improves user experience. Without caching, large-scale applications like YouTube, Amazon, or Google Maps simply would not be able to serve millions of users efficiently. Now a cache has limited space. Once it gets full, we need a smart way to decide which item to remove to make room for new data. These rules are called eviction policies. Some popular strategies are FIFO, first in first out, LRU, least recently used, LFU, least frequently used, and even random eviction. But in most production systems, LRU and LFU dominate because they strike a good balance between complexity and efficiency. Let's start with LRU, least recently used cache. Think about it like this. You have a pile of papers on your desk. The paper you haven't touched in a long time is likely the least important. Similarly, in an LRU cache, the system removes the least recently accessed item when the cache fills up. It's efficient, intuitive, and widely used in real-world systems like web browsers, while cache your recently visited web pages. To implement LRU cache efficiently, we need constant time operations for both accessing and inserting items. To achieve this, we combine two data structures, a hash map and a doubly linked list. The hash map allows fast access to cache entries by key. The doubly linked list keeps track of the usage order with the most recently used items at the front and least recently used at the back. When an item is accessed, we move into to the front. When we need to evict, we simply remove the tail node. This way LRU operations remain super fast and scalable. Now let's move to LFU, least frequently used cache. Here we don't care about how recently an item was used, but how frequently it has been accessed. The item with the fewest accesses gets evicted fast. Think of a library where books that are checked out the least are sold off to make room for new arrivals. LFU is ideal when you want to prioritize items that are more popular over time, not just recently used. LFU is a bit more complex to implement than LRU. We need to track not only the items but also their access frequencies. To do this efficiently, we use two hash maps. One maps keys to nodes so we can quickly find the data by key. Another maps frequencies to this linked list of nodes so we know all items at a given frequency. Plus, we maintain a minimum frequency tracker. This way, inserting, accessing, and evicting elements all happen in constant time. It's tricky but incredibly powerful. Now, designing LRU and LFU sounds simple in theory, but in practice, several challenges appears. We must ensure that every get and put operation runs in constant time. Updating linked lists and frequency counters without bugs is tricky. Also, ensuring correctness during evictions, especially in concurrent environments, requires careful handling. In real-world systems, multiple threads often access the same cache simultaneously. Without proper synchronization, the cache could easily get into an inconsistent state, returning wrong results or even crashing. To make caches thread-safe, we can use synchronized methods, locks like read-write lock, or thread-safe collections from concurrent libraries. Thread safety is non-negotiable in high-performance production-grade caches. As user base grows, a single cache server might become a bottleneck. That's when we introduce distributed caching, where cache is spread across multiple nodes or servers. Tools like Redis and Memcached allow horizontal scaling of caches. We must also implement smart cache invalidation strategies, write through, write around, and write back caching to ensure that the system stays consistent with the underlying data source. Designing for scalability requires thinking about network latency, partitioning, consistency, and fault tolerance. Now it's your turn. You will first build an LRU cache using a hash map and a doubly linked list. Once you are confident, you will implement an LFU cache with two hash maps and frequency lists. For those who want an extra challenge, try designing an iCache interface and implement eviction policy classes for LRU and LFU separately, following the open-closed principle. For homework, enhance your cache to include a time to live feature where each item automatically expires after a certain time. Explore large-scale distributed cache designs, especially how caches are sharded across nodes using techniques like consistent hashing. Finally, study consistency models for caches. When should you prioritize fresh data versus quick availability? Today, you have learned how LRU and LFU caching system work under the hood, how they are designed for constant time operations, and why they are so critical for system performance. Mastering these cache systems will make you a much stronger backend or system design engineer. Remember, caching is simple in concept, but excellence lies in efficient and scalable design. That brings us to the end of today's session. I hope you loved learning about cache design. Always remember, great caching strategies can be the difference between a slow, laggy system and a lightning fast one. Keep practicing and experimenting with different cache designs. I will see you in the next class. Until then, happy designing and thank you for your attention.